Okay, good morning, everybody. It gives me great pleasure to welcome you all to the last morning session of the last day of this conference. Today, our first speaker is Professor Joseph. And he will be speaking on asymptotics of the second moments for GL3L functions. Please, Professor Joseph, you can start.
Okay, yeah, thank you for the introduction. So yeah, today we're going to talk about this asymptotics of the second moment of GL3 twisted L functions. Okay, so unfortunately there will be no delta method, like spoiler, involved in this talk, but it's definitely in the related stuff as in the title of the conference. Okay, so yeah, so this is ongoing joint work with Junxian Li. Okay. Okay, so here's the outline of today's talk. Okay, so first I'll quickly go over some preliminaries. Okay, and most of the preliminaries you probably have heard already in this workshop or conference or by other people. But I just want to very quickly go through all of them just to recall your memory and make sure the background materials is set here. And then I'll talk about the previous triumphs on this second moment of GL3 twisted L functions. And then I'll state my main result. Okay, and then I'll move on to discuss the proof, and I'll split the proof in actually two sections. Okay, so the first section is that we are essentially going to reduce what we are studying into sums of hypercrystalline sums. Okay, so if you haven't heard of that, that's okay. We will talk about what they are. Okay, and then the second part of the proof is to analyze the sum over hypercrystalline sums by using the GL3 Kuznesov formula. Okay, so and then finally, if time permits, I'll mention one technical difficulty that we are dealing with, and yeah, and that's the flow of today's talk. Okay, so let's jump into the preliminaries right now. Okay, so preliminaries. Okay, so just very quickly, we just quickly mentioned, like you guys have heard this many times already in this conference. So what are L functions? To say in a very simple manner, L functions are generalizations of the Riemann zeta function, and then we call a function L as pi to be a degree M L function if it has okay, let me use my pen here, maybe like this. Okay, so if we have a Dirichlet series like this, and then you have an Euler product like this, and there are m factors in total, then we call it a degree ML function. Okay, in particular, in this talk, I'll mention GL3 L function, which is a degree 3 L function. So we have free stuff in this Euler product. Okay, and then we of course need the L function to have some analytic continuation to the whole complex plane, and then we also need a functional equation that relates the L function value at S and 1 minus S, so we can go back and forth. Okay. So what are moments of L functions? Okay, so this is, I guess, in the topic of Matt's lecture series. Okay, so what happens is a lot of arithmetic object that we are interested in ultimately ties to some special values of the L function. And the special values are usually the critical value, like L1/2 of pi, or on the critical line, this kind of particular values. Okay, and then to study this kind of things, okay, so one way is to study the moments. Okay, so there are multiple ways you can do to study this critical value of L function. And in this conference, you have seen multiple times, like you can use, for example, delta method to study it also. Okay, and another approach is you can do moments. Okay, so you can if you want to study this this critical value, this particular value, you can put the absolute value and raise the whole thing to the power m, and then you can sum over appropriate family, and then maybe you can analyze this average or this sum over the family of this critical value in a good manner, and then you can get some kind of value distribution or whatever you want. Like there are many applications of studying moments, and they are kind of covered in Matt's lecture series, and maybe also other people's talk already. Okay, so to study this kind of moments or critical values of L function, one standard opening move is to use the approximate functional equation, okay, which we can rewrite the L function, the critical value of the L function as two sums, and they are essentially of very similar shape except of a difference of a root number there. This epsilon pi that appears, okay, in the second guy, okay. But essentially we can, instead of studying this critical value, we study a truncated sum of the Fourier coefficients of this form pi, okay. And we know the truncation of this sum, which is going up to the square root of the conductor of the pi, okay, which is a measurement of complexity of your form pi, okay. Okay, so these are the kind of the preliminaries that we need to use, right? So, and then now I'm going to mention the previous triumphs and main results. Okay, so what do we know previously for this second moment of GL3 twisted L functions? Okay, so if your form, so in particular, we are looking at this L of 1/2 f cross chi, where chi is some multiplicative or Dirichlet character, okay? And the f is a GL3 form, okay? So when f is specialized to be 1 + 1 + 1, the isobaric sum of 3 ones, okay? This is essentially the sixth moment of the Dirichlet L function, because this, when f is 1 + 1 + 1, this L of 1/2 f cross chi is really just L of 1/2, like the Dirichlet L function cube. Okay, so the second moment of this, of the Dirichlet L function cube, would be the sixth moment of this Dirichlet L function. Okay, so the first result was shown by Huxley, okay, quite some years ago, that you can get sharp upper bound for this Dirichlet, the sixth moment of Dirichlet L function, okay, when you sum over the chi, okay, and also the modulus. Okay, so if you sum over both, like it's kind of a bigger family, like, so you need like that big of a family, then you can get the correct sharp upper bound. Okay, and actually he didn't just do the sixth moment, he did it like he did the second, fourth, sixth, and eighth moment, I believe. Okay, so but I'm just focusing on the sixth moment because this corresponds to what we are doing right now, the second moment of GL3 twisted L functions. Okay, and then the second result is by Kummari, Leung, and Ramanujan, who showed that you can actually get asymptotics. So not just sharp upper bound, but you can get asymptotics if you also include a T integral. Okay, so if you integrate along the critical line, okay, then you can get asymptotics. And this T integral, okay, here, you may ask, okay, what is the size of this T integral? The T integral is actually very small. Okay, so you just need a very small window of T integral around 0 to let you get asymptotics. This is because if I write it like this here, you can see this is written in terms of the completed L function. Okay, so the completed L function has a gamma factor that decays exponentially as T goes big. Okay, so this integral here is really localized, essentially localized around 0 by maybe q to the epsilon or whatever parameter, like goes like, yeah, q to the epsilon. Okay, yeah, so this is a very small integral that you need to add. Again, once you have the integral, you can get asymptotics. Okay, and very recently, like I think 2 months ago or something like that, it appears on arXiv. Okay, so Chandy Shenali, Kaisa Motomaki, and Maxim Resville show that you can actually remove this T integral and still get the asymptotics. Okay, so this T integral can now be removed. Okay, and you can still get the asymptotics here. Okay, oh, oops. Sorry. Okay, back here. Okay, so so now you may ask, okay, what if F is a GL3 custom in general? Okay, so we showed the previous result of this previous result work for F being 1 + 1 + 1, meaning it's about the sixth moment of Dirichlet L function. Okay, so maybe one comment I should make here. So this last result by these 4 authors actually holds for if your F is a GL2 + 1. Okay, so it works for GL2 + 1. You don't need 1 + 1 + 1 to make the proof works. Okay, so but however, none of these results work for F being a general GL3 cusp form. Okay, so what if F is a GL3 cusp form? Okay, so from what I know, nothing is really written down. Okay, but people do know that asymptotics can be done if you have the t integral. Okay, so it's not that hard to get the asymptotics too if you have the t integral. Okay, and actually we will kind of see this. Okay, so in the proof that I'm going to show you of our main result, okay, we will see in the middle that at some steps you can essentially get the asymptotics if you have the t integral, and then you can also easily get the upper bound q to the 2 plus epsilon. Probably you can also push the log factor if you want to, but you can get the upper bound with q to the 2 plus epsilon. It's also not hard even without the t integral. Okay. Okay, but now is our main results that I'm going to share today. Okay, this is still working in progress with Junsen Lee. Okay, so let F be a geo-free class form that assume GRH. Okay, so none of the previous result. Oh my God, what happened? Okay, back to here. Okay, that's something. Okay, so here we need to assume GRH. So none of the previous result I mentioned about this F being 1 plus 1 plus 1 being the 6th moment of the L function, or actually the 4 first paper actually work for 2 plus 1. So all of them doesn't require GRH, but our result requires GRH. Okay, so we need GRH. Okay, I'll mention what we actually need. Okay, when we go through the proof. Okay, but under GRH, then we can do the asymptotics for the second moment of GL3 twisted by chi. Okay, so same family, summing over chi and summing over q. We do not need the t integral. Okay, and we can get the asymptotics. Okay. So right now we can, in the sketch, we can get power saving with the saving being 1/6. Okay. But again, this kind of saving may be worse in reality when we really work out through all the details. But this is what the current sketch yields, and this should be the ultimate saving you can get with this method. Like you probably can't get beyond this using our method. Okay. So any questions so far? Is everything good? Okay. So if there is no question, then I'll move on to discuss the proof of this statement here. Okay, so this asymptotics of the second moment. Okay, so as I mentioned earlier, we are going to split. Why is this? Okay, we are going to split this proof into two parts. Okay, so the first part is more like a more standard maneuver. Okay, and we can relate what we are studying to the study of sums over hypercrystalline sums. Okay. Okay, so as I mentioned earlier in the preliminary section, okay, so the first step we're going to do is we open up the L function value by the approximate function equation. Okay, so we do not open the L function individually, okay, but we open the whole norm square of the L function as a whole thing, okay, by the approximate function equation. Okay, so doing so essentially lead us to the following structure here. Okay, so this is still the family that we are summing over. So this norm square get replaced by this thing here. Okay, so which is this sum over mn going up to q cube, and then we have the GL3 Fourier coefficients, and then we have the chi. Okay, and then the normalization at 1/2. Okay, okay, so this is what the approximate function equation gives us. Okay. So the good thing about opening the approximate function equation on this whole thing being a norm square is that we don't need to care about the root number, because the root number for this guy is 1. Okay, so as the whole thing, like the norm square. Okay, so there's essentially only one piece that we have to deal with. Okay, however, the disadvantage of doing so is that we now have m and n going up to q cube here. Okay, so we do not have, for example, we do not have the restriction that m and n both go up to q to the 3/2, but they together go up to q cube, meaning one of them can be extremely huge. It can be biased towards one of them. So it can have a very big m and a very small n, and etc. Okay, so this is the disadvantage of opening the whole thing as a norm square. Okay, but because of the root number, we want to open the whole thing as a norm square. Okay, so if you open up only just the L 1/2 as a thing, and then you do L 1/2 multiplied by L 1/2 bar, then you have to deal with the root number although you have the truncation that m and n both goes up to q to the 3 half. Okay? And we don't want to deal with the root number, so we choose to do it this way. Okay, but the fact that m and n can be biased towards one of them, like one of them can be very big, it's actually going to bite us back, like it creates the hard case. Okay, but anyway, so this is what we're going to do. Okay, so if you look at this, and then the main term, okay, as expected, would be given by the term m equaling n. Okay, so you can compute the main term as usual. Okay, so the main term computation is easier when you have a cusp form, actually. So if you have like sigma mod DKL function, then you have to do more things about the main term. But if you have cusp form, the main term is actually easier. Okay, it only comes from this m equaling n, essentially. Okay, so you can compute that. That's kind of standard. And then now we move on to try to compute the error term and try to bound it. Okay, so we have to now focus on the case where m is not equal to n. Okay, so once you sum over chi, okay, sum over the character here, okay, and then you do dyadic subdivision on all this m and n, okay, because now we are only seeking upper bound right now. So we are free to do all this dyadic subdivision and stuff like that. And we are trying to also hit like power saving, so we don't care about the loss of like log or whatever. Okay, so we do dyadic subdivision on all these things. Okay, now you get down to this structure here. Okay, so the sum over chi becomes a congruence condition, so you get m is congruent to n mod q. Okay, and then you, as usual, you have the GL3 coefficients. Okay, and then essentially you have to show that this is bounded by something less than q squared. Okay, so the goal is to show that this structure right here is less than q to the q squared. Okay, so this is what we are trying to do now. Okay, we have to bound this. Essentially, you can see that this is a shifted sum, right? Because m and n is congruent to each other mod q, and then you can view m as like n plus q times some integer. Okay, so this is dealing with a shifted sum. Okay, so there are some similarities, like for example with Matt's talk about work for the yeah. But anyway, so we now have to deal with this shifted sum. Okay. Okay, so now we go on to study what we have. Okay, so so now we're going to do a divisor switching trick when for a certain size of m and n. Okay, so without loss of generality, we can assume that one of them is bigger. Let's say m is bigger than or equal to n because they are completely symmetric. Okay, so the m and n. Okay, and then if m is actually less than q squared, okay, we try to do a divisor switching trick. Okay, so you may ask, what is a divisor switching trick? Okay, so this is a kind of a very simple idea. If you have a congruence mod q, so here my m and n are congruent to each other mod q, and then if you also sum over the modulus of the congruence, then you can do this trick. Okay, so what you can do is you rewrite the congruence condition of m being n mod, so m congruent to n mod q, to be m minus n equal to q times r. Okay, and then the r goes up to the size of the equation divided by your modulus q. Okay, so the size of the equation is m because we assume m is the bigger guy. Okay, so that's why r goes up to m over q. So I guess I shouldn't write like r asymptotic because r goes up to that. R can even be 0. Okay, but it doesn't really matter. This is just a sketch, and it's just a demonstration of ideas here. Okay, so so you write it as m minus n equal to q times r, and now you can sum over q instead of summing over r. Okay, so you sum over q, summing over the modulus essentially tells you that this m minus n is equal to qr is the same as m congruent to n mod r. Okay, so so now you change your congruence condition mod q into a congruence condition mod r, and now what is the size of r? So r is m over q, the size of the equation divided by your original modulus. Okay, so in analytic number theory, we often loves to have things that have smaller conductor. Okay, meaning the complexity is kind of lower, and the complexity for this kind of congruence condition is how big the modulus is. Okay, so you want to do this trick when q is actually bigger than r, which means you want to do this when q is bigger than so you want to do this when q is bigger than m over q, okay, which is precisely when m is less than q squared. Okay, so you want to do this trick when m is less than q squared. Okay, so we do this trick for m is less than q squared, and then we don't do it when m is bigger than q squared. Okay, and what happens if you do this? Okay, so this gives again some very similar congruence condition structure, congruence kind of shifted sum like that. Okay, so this will tell us essentially the hardest case is actually not at the balance case. The balance case being m and n being both q to the 3/2. Okay, but the hardest case is actually m being q squared and n being q. Okay, because this is the place where divisor switching trick doesn't work, barely. Okay, yeah. Okay, so this is kind of the hardest case, and in Sketch we will focus on this case. Okay, and right here I can answer one of the comment earlier that I made, that if you have a t integral, then computing the asymptotics is it's kind of easier. And you can see the reason here, because when you have the t integral in your second moment, the t integral forces your m and n to be of the same size, meaning both of them goes up to at most q to the 3/2. And the divisor switching trick is very good to deal with this range. Okay, so that made the whole problem easier if you have a t integral. Okay, but we don't, so we are forced to deal with this hardest case where it can be unbiased like this. So we focus on m being q squared and n being q. Okay, so in this case, we don't need to do divisor switching trick. Okay, so they are the same when you do it. Okay, so now this is the structure. The first line is the structure that we have when I plug in m being q squared and n being q. Okay, and again, our goal is to show that this is bounded by q squared. Okay, so we have to show that this is less than q squared. Okay, so now we start our maneuvers. Okay, kind of standard maneuvers. So we can detect the congruence condition by multiplicative characters or additive characters. It's up to you. So in the paper, we are going to use multiplicative characters, but in the presentation here, I think it may be easy to see the character sum structure using additive characters. I'm going to use additive characters here. Okay, but in reality, when you write down the details, multiplicative character is probably easier actually. Okay, but anyway, so here I use the additive character to show the concept. Okay, so we rewrite the congruence condition of m being n mod q as this additive thing here. Right, so okay. So plug this thing into this congruence condition right here, okay? And now we can do Ramanujan summation, okay? So on the m sum, because the m sum is the long one, okay? So if you apply on the n sum, it's not that good because of how the length is too short to begin with, okay? So we apply Ramanujan summation on the m sum, the long one, but not the n sum, okay? If you do multiplicative characters, then you're doing functional equation, but whatever. So it's kind of the same thing, okay? So once you do the Ramanujan summation on the m sum, what happens is the new length goes from, so the length goes from q squared originally, and now the conductor is, because it's a geometry, so the modulus is q, so it's q cubed over the original length. So it goes from q squared to q. Okay, so the new length becomes q, and you can see everything is of size q right now. Okay, and then if you do the normalization correctly, okay, if you trust my computation, then the Ramanujan summation gives you this structure right here at the end of this page. Okay, so yeah, okay. So now you look at this, okay, and if you are familiar with this kind of things, you will be able to identify what this character sum is. Okay, this is precisely like this alpha beta mod q sum is precisely the hyperclusterman sum. Okay, so yeah, okay, so this guy here is precisely the hyperclusterman sum. This is the GL3 version of the Clusterman sum essentially. Okay, so I guess for people who may not have seen this kind of things, okay, so the normal Clusterman sum looks something like this. Okay, so sum over alpha mod c e of co-prime. Okay, so alpha m plus alpha bar n over c. Okay, so this is the GL2 or the standard Clusterman sum. Okay, so you have alpha and alpha bar. Okay, and then here, what happens in GL3 is you have, instead of just one alpha sum, you have alpha and beta, and then you have alpha beta and alpha beta bar. Okay, so I mean, it's kind of believable that this is kind of like a generalization, And it's true, like this is the GL3 version because this appears in the GL3 Poincare series, and then also in the GL3 Kuznetsov formula. So this is the correct analog for the GL3 Klustermann sum. Okay, but anyway, so we see that the hyperklustermann sum appears. This GL3 Klustermann sum that we call hyperklustermann sum appears. Okay, so this is the structure that we want to study. Okay, so I just clean up the notation here and rewrite the alpha beta sum as with the correct normalization as the hyperklustermann sum or the GL3 Klustermann sum. So we use KL3 to say this is the GL3 Klustermann sum. Okay, so now with this normalized to be size 1, okay, what we need to do is, okay, so the trivial bound right now you can check. Okay, so you just check like there's a 1 over root q and then q, q, and q. Okay, so you can check that this is trivially bounded by q to the 5/2, maybe plus epsilon, I don't care. Okay. But we have to show that this is bounded by q squared. Okay, so we are square root away, okay, from the trivial bound. Okay, so what happens is what you can do is you can actually use Cauchy-Schwarz to take out, let's say, m and q. Okay, and you can actually get down to the boundary. You can actually save square root q more. Okay, you can show that this is bounded by q squared. Okay, so this is the point where I answered the other comment that I made earlier, that if you just want the upper bound of q to the 2 plus epsilon, it's actually not hard. Okay, right here you can get q to the 2 plus epsilon. Okay. And then at this point, we look at this guy here. Okay, so we just have to do a little bit better than the Cauchy-Schwarz bound. Okay. And then we started this project like I think almost 2 years ago. Okay, 1 year something ago. Okay, and then we in the early stage we got down to this, and we were like, okay, we should be able to get this. Like it's just barely there. Okay, and then we were stuck for months. Okay, we don't know how to deal with this and show that this is less than q squared. Okay, until one day we realized, oh, okay, we should use the sum over hyperklustermann sum. Like we try a lot of tricks to adjust the setup and stuff like that, but at the end, okay, we realized, okay, so we should try to use this sum over hyperklustermann sum, okay, to do something. Okay, so this is the first part of the proof. Okay, we go from the second moment and then we analyze the error term. We get down to this sum over hyperklustermann sum that we have to study. Okay, so for people who are experienced with this kind of things, okay, so you can kind of guess what should happen, right? So if you want to study sums over normal Klustermann sum, you need to use the GL2 Kuznetsov formula. Okay, so now we want to study sums over hyperklustermann sums, which are GL3 people, like GL3 guys. Okay, you want to use the GL3 Kuznetsov. Okay, so this brings us to the next part of the proof. Okay, the second part of the proof. We try to use the GL3 Kuznetsov formula to study the sum over hyperklustermann sums. Okay, so let me quickly recall, okay, what are Kuznetsov formula and how we actually use them to study Klustermann sums and stuff like that. Okay, so Kuznetsov trace formula is like a spectral identity. It's a formula that relates two sides. Okay, so you have the spectral sum on one side, which consists of like your cusp form, Eisenstein series, okay, things that lives on the GLN like space, okay. And then if you have the whole family, the correct whole family, and then you sum over all the stuff, okay, then you can evaluate that explicitly, and you can go to the right-hand side, which is the geometric side. Okay, so the geometric side, I mean, it's kind of like quote unquote the simple side in some sense, but it's actually not simple, but it's explicit. Okay, so you can write down what the geometric side is. Like it consists of some delta term, which is just some restriction of your variables, and then you have the Klustermann sums. Okay, so they are explicit. You can write precisely what they are. Okay, so you know what they are, but they of course are still hard to study. Okay, but regardless, okay, you can go from one to the other. So if you want to study like cusp form or Eisenstein series, okay, then you can use this, and then you can go to study this kind of geometric side. Okay, so maybe you can have some ways to analyze the geometric side, and you can get some results on the left-hand side. Okay. On the other hand, if you start from like crystal sums or this kind of things, and then you want to study them, then you can pass to the left-hand side and study the spectral side instead, and then hopefully you can analyze those and then get some results on the crystal sums. Okay, so this is a formula that allows you to, it's an equality, so you can go from left to right, right to left. Okay, so well, in GL2, okay, the special case, so one special case is the Peterson trace formula. Okay, if you sum over all the holomorphic forms, then you can get whatever evaluation. So you can see there's a delta term that is just a restriction of your variable, meaning like you get 0 unless m is equal to n. Okay? And then you have a sum over normal crystal sums. Okay. And then the more general format is the Kuznetsov trace formula that incorporates the whole family. Okay, so so one way to write down the Kuznetsov trace formula, the GL21, is that you start from the sum over the crystal sums. Okay, then you can write it. So if you start from the geometric side, you can write it as the spectral side, which consists of all the like the correct family, the holomorphic form, the mask form, and also the Eisenstein series. Okay, so you get this evaluation. Okay. So now we jump to the GL3 version. Okay, so the GL3 version looks a little bit more more complicated. Okay, but it's still of this kind of structure. You have the spectral side and geometric side, and the spectral side, you can see the left-hand side consists of your C, which is the cusp forms. Okay, and then it consists of the Eisenstein series, which has minimal Eisenstein series, which correspond to things that come from GL1 plus GL1 plus GL1. Okay, and then you also have the maximum Eisenstein series, which consists of things that comes from the GL2 plus 1. Okay, so essentially it's just a decomposition of or partition of integers, right? 3 is 3 plus 0. It's also 2 plus 1. It's also 1 plus 1 plus 1. So you get all the things that live in the GL3 world. Okay, so they can come from lower rank stuff. Okay, so that's the spectral side. Okay, and the geometric side is, again, there is some delta term and some crystal sum, which I wrote down here. Okay, so they look kind of crazy, but still, okay, so they are whatever they are. Okay, so the delta term is, again, some simple thing that restricts some of your variables. Okay, and then you have your S4 and S5. Okay, they are symmetric with respect to each other. Okay, and they are essentially the hypercrystalline sums, although it doesn't look like it. Okay, but in some special form, like if you, for example, you plug in n1 equals to m2 here, so just assume a lot of the variables are 1. Okay, so if n1 is m2, then this gets discarded. So this is really a character sum mod d. Okay, and then you can see the alpha, and then if you change beta to beta bar, maybe. Okay, so then you can see the alpha beta and alpha beta bar. Okay, precisely the what the hypercrystalline sum should look like. Okay, so the S4 and S5 consists of the hypercrystalline sums that we are looking for. Okay, so they appear here. But the trouble thing is, so the GL2 version only consists of the normal crystalline sum, but the GL3 versions not just only consists of hypercrystalline sum, they also consist of a crystalline sum that correspond to the long while element. Okay, is this S6 here. Okay, and this is a beast. Okay, this is a very annoying guy. It's a monster. Okay, so the long while element crystalline sum, okay, actually consists of 2 modulus. Okay, so the previous hypercrystalline sum and stuff like that only consists of the modulus d, right? So you can see it's just this sum over d. Okay, so there's only this one modulus. But for the long while element crystalline sum guy, it consists of 2 modulus. Okay, d1 and d2. And here, this is the long while element crystalline sum essentially. Okay, so what I'm writing down is a result by Kirao and Nakatsuchi, who wrote down this decomposition of the long while element crystalline sum as a product of 2 normal GL2 crystalline sum. Okay, so it looks less horrible, right? So you can write it as the normal crystalline sum, a product of these 2. Okay, but the problem is, or the difficulty once you try dealing with it, is that this modulus is being intertwined together. Okay, so both of this crystalline sum has d1 and d2 inside. Okay, so they're intertwined and it's becomes super complicated. Okay, so but this is what it is. Okay, So now, okay, so now we try to use this Kuznetsov formula to study hypercrystalline sums. Okay, so same as the GL2 version, right? So if you want to study sums of a crystalline sum, you try to pick up the sum of a crystalline sum and express the sum of a crystalline sum as the rest of the guys. Okay, and then yeah, you just kind of replace the sum of a crystalline sum by the rest of the stuff, okay, which is the spectral things. Okay, so you may want to just try to do this thing right here. Okay, so for our result, right? So we were trying to study sums of a hypercrystalline sum. Then, well, why do we not just take out the S4 and S5, which consists of the hypercrystalline sums, right? The things that we need. Okay, and then put it on one side and express it as the other guys, right? The cusp form, the Eisenstein series, the delta, and also the S6, right? So, well, this is yeah, of course, that should be the first natural way to do this kind of things, okay? But what happens is once you try to do this, as I mentioned, S6 is a monster, okay? So S6, the trivial bound for S6 is actually huge, okay? So if you just put the contribution of S6 is trivially huge. So you need to really be able to exploit a lot of the structures from S6 together with your original structure and to hope for some good result by replacing the hypercrystalline sum with this kind of things. Okay, so yeah, so here I wrote down the problem is that S6 is just hard to control. It's just huge and it's hard to analyze because the D1 and D2, the modulus are intertwined together. It's hard to do any nice analysis on it. Okay. However, there's a light in the way. Okay. So what happens is we found out, okay, so 2 years ago when we were starting this project, okay, there is a result by Jack Butkain, okay, who wrote down, okay, actually, if you can, you can choose the test function in a very nice manner, and you can incorporate the parameter in the test function, okay, and it will allow you to actually trivially reduce the contribution of S6. Okay, so trivially, the contribution of S6 is smaller. Actually, what the parameter does is actually it just reduces the length of one of the moduli, one of them, moduli in one of D1 or D2. Okay, in S6, the long-wide element crystalline sum. Okay, so but you may say, okay, of course, like I can't just freely reduce it. Okay, there is nothing for free in this world. Okay, so there is a cost when you put such a parameter in the test function that reduce the contribution of S6. Okay, so what it does, it will increase the contribution of the cusp form. So you trivially actually has to sum over bigger spectral parameters of your cusp form. Okay, so increase that contribution. Okay, so we can kind of rebalance a little bit the contribution of S6 and the cusp form, okay, by doing Butkain's argument, okay, or his choice of test function. Okay, so now we're going to do that. Okay, so back to what we had. Okay, so what we had was this structure here, and then with a sum over hypercrystalline sums. Okay, that was what we had. Okay, so now I'm just applying essentially Butkain's work. Okay, so essentially the GL3 Kuznetsov formula, but also with his choice of test function. Okay, and what happens is essentially you will get down to two structure. Okay, so one comes from the spectral side, this F. Okay, so the contribution of the essentially the cusp form. Okay. And also the other term comes from the contribution of S6, the long-wide element crystalline sum. Okay, so we are replacing this sum over hypercrystalline sums by this guy here and also this guy here. Okay, so which is the spectral thing and also the long-wide element crystalline sum thing. Okay, so now we just have to bound these two things. Okay, so well, you may ask, okay, so how can we bound this kind of thing? So let's take a look. Okay, so let's first focus on the F. Okay, so the spectral side. So F is something like this. Okay, so this lambda C is some GL3 forms essentially. Okay, And there is a average over the family here. So this is the family average of this G of three forms. Okay, so the sum over the G of three forms. Okay, and then this was our original thing. Okay, so what we are going to do here is that now we can, so right here, like if you just bound this trivially, this is bad. Okay, so the only thing we can use right now is the M and N sum. Okay, so these are the two things that we have in our hands right now to leverage or to do something. Okay, so how can we use the M and N sum? Okay, so if you look at the M and N sum individually, okay, each sum is really, so for example, the M sum is a G of three coefficient multiplied by another G of three coefficient. Okay, so now if you have a G of three coefficient multiplied by the other G of three coefficient, it is almost, okay, it's not exactly, so you have to patch it up, but it is almost the GL3 cross GL3L function. Okay, so we can kind of combine these two. Okay, and then we can combine the N guy. Okay, so each of them forms a GL3 cross GL3L function where the GL3, like it's F cross this C. Okay, GL3 cross GL3. Okay, so these two sums becomes essentially the GL3 cross GL3L function. And now this is where we apply GLH. Okay, so once we pass everything to the L function, we can use our favorite hypothesis GLH to bound it. Okay, so yeah, so we apply GLH, which technically here we only need Lindelof on average because there is a average here. There is a family here. Okay, so we actually only need Lindelof on average, but it's a Lindelof on average on GL3 cross GL3L function where one of the GL3 has spectral parameters. Okay, so it's a quite complicated family, but technically we only need Lindelof on average. Okay, so once you do this, we can bound this F and it will be satisfactory. Okay, so that's kind of the idea here. Okay, that's how we bound the spectral side. Okay. Okay, so now let's go to the off-diagonal side. Okay, so I think I still have a few minutes or so. Okay, so so this is the off-diagonal side. Okay, so again, this is the normal element Christman sums here. This was the original thing essentially up to some correct normalization. So as I mentioned earlier, this normal element Christman sum decomposed into two Christman sums. Okay, so the two normal Christman sums by the work of Kirao and Nakasuji. Okay, and what happens is if you now try to do something here, okay, again, trivially is bad. Okay, so the effect of Butkin's test function allows us to reduce the length of one of the moduli. Okay, so this, let's say C1. Okay, in this write up, this is actually reducing C1. Okay, so what happens is if I have a parameter x in the test function, then my moduli C1 and C2 is C2 is of size Q square and C1 is of size Q over X essentially. Okay, and then you may then immediately say, oh, what if X goes up to Q? Like, what if X is bigger than Q? Okay, so actually you can choose X to be bigger than Q, and it's explained in Butkin's paper that if you choose X to be bigger than Q, then there is no such contribution at all. Okay. And that would be perfect. Like we would be very happy that we don't have to deal with this. But unfortunately, if you choose X to be bigger than Q, the spectral side blows up. Okay, it's no longer satisfactory if X is bigger than Q. So we are forced to choose X to be smaller. So we have to still deal with this this normal element Christman sum. Okay, so we choose X to be less than Q, we still have to do this, but we still choose X to be some size so that it reduces the modulus C1. Okay, so now we proceed. Okay, so we're kind of trying to do the same idea. So now, okay, back to here maybe. Okay, so now we have sum over C1 and C2, and this is the I mean the Christman sum is just two Christman sums. Okay, so we can now make use of the longest C2 sum. We sum over C2, which is again the sum over GL2, the sum over GL2 Christman sum, or the standard Christman sum. And we know what we are going to do, right? So we're going to use GL2 Kuznetsov to study the sums over normal Christman sums, which is kind of well understood in the literature, how to do that. Okay, so we do the GL2 Kuznetsov to study to sum over the C2. Okay. And now the sum over C2, which is like this crystal sum here, okay, it will translate the whole thing to the spectral side, which gives us GO2 Fourier coefficients or GO2L functions here, okay. Ultimately, we apply the same idea. Once we get everything down to just Fourier coefficients of GO3 or GO2L functions, okay, we again look at the M sum and N sum separately, combine them. This time we have GO3 and GO2 instead of GO3 and GO3, so it becomes a GO3 cross GO2L function. Okay, so this guy here. And again, we apply GRH, okay, best friend GRH, okay, so, and again, technically we only need Lindorff on average because we do have a family, okay, so, so this family actually can potentially be, potentially GRH is not necessary. I think there are already some work on this, on this kind of family, and yeah, that may be able to just remove the GRH right here, okay, but because this is a kind of a less involved family compared to the GL3 plus GL3, okay, but anyway, so we do the same idea, okay, so we combine, okay, use the GRH or use the Lindorff on average of this kind of L functions, we bound our long vowel element crystalline sum contribution, okay, so that's the whole proof, okay. Okay, so yeah, so let me just quickly recap, okay, what we have been doing, right? So we started with the second moment of GL3 twisted L function, okay? So we kind of open it up with approximate function equation, sum over the chi to get the congruence, so we led to a shift sum. Then we do Warnow in one of the variable, which is the longer one, okay? And we arrive at the sum over hypercrystalline sum. So to study sum over hypercrystalline sum, we use the GO3 Kuznetsov, okay? And with GO3 Kuznetsov, okay, once we pass everything to spectral stuff, we combine them together as an L function, okay? And then we use GRH or Lindblom on average, okay? So that's the whole point, okay? So that's the whole conceptual proof of this second moment, asymptotics, okay? Okay, so yeah, I think I'm almost time's up, but maybe I can just quickly mention this final part of my, there's one technical difficulty, as if the previous proof is not complicated enough, like, okay, when we figured all these things out, we were like, oh, this is kind of a huge, like, it's just kind of very complicated to get everything done, okay? But there is even one more complication, is that in reality, what happens is instead of the hypercrystalline sum of M, N, and Q, we actually have some inverse here, okay? So we have some inverse here. And this is in general, like in the generic case, this is size 1, okay? And with GRH, we can actually show that it's like, as long as this R is like slightly bigger than 1, then it's fine, like, yeah. So this is really a size 1 thing, but this size 1 thing having an inverse is giving us a huge trouble because of the fact that if you just do normal Kuznetsov, it doesn't have this inverse that appears in the hypercrystalline sum. Okay, in the it's the same case in the GO2 situation. In the GO2 situation, if you have an inverse there, what do? So you need Kuznetsov with a cups. Okay, so you need a Kuznetsov formula with the correct cups to give you crystalline sum with an inverse. Okay, so the same thing happens here. Okay, so we need the GO3 Kuznetsov with a cups. Okay, so with cups to deal with this size 1 thing. Okay, that is in the generic case, it shouldn't really matter, but we have to deal with that. Okay, so this is why kind of our, I mean, it would still take us some time before we can finish writing up this paper. Okay, so there are a lot of things that are not written down in literature. Okay, so the GL3 Kuznetsov with cups is not exactly written down in a nice format. Okay, so and yeah, okay. But that's the kind of the current stage of our project right now. Okay, but yeah, anyway, so okay, I'll end my talk here, and thank you for listening.
Okay, thank you very much for the nice lecture. Are there any questions, comments, remarks? Yeah.
Hi, Joseph.
Yep.
I sort of a maybe speculative question, but since you're learning how better to use the GL3 tools like Kuznetsov, do you feel like there's any potential hope of improving Miller's bound using any of this part of the machinery?
Right now, I don't think so. Yeah. So I tried, for example, using GL3 Kuznetsov. So for example, you can if you have, let's say, so the Mueller bound really, okay, so the Mueller bound is something like this, right? So and then n of x, and then the usual standard startup is that you want to replace this x by, let's say, a over q, something like that. Okay. And then to get the Mueller bound, you do Voronoi, and you will essentially get something like this. And q. Okay. And then now q and n will be of the same size. Okay. And this is, I think, the huge difficulty here. Okay, so having the same size of n and the moduli being the same size is extremely hard. So I tried doing something like, if you use GL3 Kuznetsov, you can, for example, sum over this an, like this family here, and you can replace this an by whatever the Kuznetsov gives you. But still, I don't see any hope right now. But we can discuss more if you are interested, and
yeah,
I can
sure.
show you something. Yeah.
Thanks.
Any other questions, remarks? Yeah.
Hi, Joseph. Great talk and great results. So I just had one quick question about using GRH or Lindelof on average towards the end. Do you need the full strength of Lindelof, or weaker exponent will do? And
weaker exponent will do, yes, but not much weaker. Yeah.
Not much weaker.
So
Yeah.
we need an extremely strong subconvex demand.
Yeah. So have you looked at techniques of Ivanich or Lewis Sarnak? They do it. They do Lindelof on average for GL2 in spectral aspect, but I believe you need something different and something much stronger, which is like GL3, something much more complicated. But have you tried looking at those things?
Yeah, I haven't, but I do believe that there is either already result or it's doable. I think there may be even some people has mentioned that there may be already results for this thing. Like so for this GL3 cross GL2, right? Really here what we need is so it's this family. So you have a level, and then you have an adventipus, and then you have this LSF. Essentially, you're doing the second moment of this family. Okay.
Right.
And I think we may be able to remove the GRH for this, because maybe there is already result for this for the sharp bound for this.
Oh, perfect. Yeah. Great. That'll
be
nice.
But definitely not the GL3 cross GL3 one. That would be.
Sure. Thank you. Thank you so much.
Yeah.
Are there any other questions? Yes.
Hi, Joseph. Can you apply balanced approximate functional equation? So what happens in that case in the very beginning? So
in the balance range, you mean?
Yeah.
So you mean
so
when
when
M
you
and N are the...
Right. So what difficulty do you get there?
Oh, I mean, you can. So in the balance, when M and N are same size, or like q to the 3/2, it's actually not that hard. Okay, so you can do the divisor switching trick, and things become very nice.
No, I meant if you just approximate the L value and then.
It's the root number.
So how bad is that? It's
So
not.
yeah, what happens is you will get a root number, probably like epsilon chi. Is it cube or something? I forgot. Like maybe probably it's a cube, like because of GL3.
Right.
So what happens is, so here we make crucial use of the fact that when you sum over chi, you get the congruence, right? So once you have a root number, the piece with a root number, when you sum over chi, it actually gives you again the hyperclusterman sum. So yeah, again stuck with this hyperclusterman sum. Yeah.
Okay. And I think Jungxian once mentioned, so if you allow factorization in capital Q, then you don't need GRH, right?
So that is for another result, I think. Yeah. So
What was that?
so that is, I think, so he is or she is working with Yung Shaolin and Shannon Lee
Yeah.
on this. Okay, maybe I'll tell you later. I
I
say
think it
something
was.
wrong
No,
in the
no, no, no.
recorded.
So it was different. Yeah, it was different. It was
Yeah,
like
it's a different thing, but yeah,
you have
they're
pi
still also
times.
studying some moment like this. Okay, but it's a different moment. Yeah,
So like 3 + 1 family. Yeah. Okay.
something like that. Yes, yes, yeah.
Okay. Thanks.
Mhm.
Are there any other questions? Okay, if not, let us thank the speaker again.